Student, as we earlier learned about magnetic field produced due to a circular loop when current was passed through it. Now what we are going to do, we are going to consider n number of turns. So n number of turns add up to give more magnetic field with more strength. Let us talk about magnetic field due to a current in a solenoid. The first question arises in our mind that what do you mean by solenoid? Solenoid is a coil of many circular turns. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. As you have seen the shape of a cylinder. Shape of a cylinder is called a solenoid. I repeat, a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid.
Take a long coil with many circular turns of insulated copper wrapped closely in the shape of a cylinder. This type of coil is called as a solenoid. The electromagnetic effect of a solenoid is used in several appliances. Let us pass electric current through the solenoid and observe the pattern of magnetic field lines demonstrated here. The magnetic field lines in a solenoid are same as in a bar magnet. They pass through the solenoid and return from the other end. The field lines inside the solenoid are parallel to each other. The parallel lines will have the same magnitude of the magnetic field. That is why the solenoid has a uniform magnetic field. If we suspend this current-carrying solenoid freely, it rests pointing north and south, just like the suspended magnetic bar does. It shows that on passing electric current, the solenoid turns to a magnet having north and south poles. When we take a piece of soft iron inside this coil, the iron piece is pulled inside. The electromagnetic effect performs the mechanical function of pulling. The system of a coil with soft iron core is used for several electromechanical applications, such as start or stop actions for valves of the dishwashers, starters of vehicles, pull and push agents of the door locks, etc. The current-carrying solenoid converts the soft iron into an electromagnet. When the current is stopped, the solenoid is demagnetized. Even the soft iron core also loses its magnetism.
Students, we have drawn one circuit, that is a coil which is wrapped, or let us say wound, in the shape of a cylinder, and when current is passed while connecting it with a battery, the current which was flowing in a cylindrical shape was representing a type of magnetic field getting generated. So as we are drawing a magnetic field here, it is closely related to the magnetic field which we earlier drawn for a bar magnet. So there is a comparison that when you compare the magnetic field lines produced by a solenoid, it is nearly same as that of magnetic field lines of a bar magnet. I will mention one more thing. When you closely take a look inside the solenoid, then magnetic field lines inside the solenoid are parallel to each other and representing that all the direction of magnetic field lines are same, as well as they are parallel to each other, representing uniformity. That means inside the solenoid, magnetic field is always uniform in nature. So we can say that solenoid works as a magnet. And let me tell you one thing, that if you want to make an electromagnet, keep a soft iron core. You are hearing clearly? Soft iron core. Soft iron core represents soft, which can be easily magnetized. The word soft represents easily magnetized, which can be easily magnetized. So I am keeping one soft iron core in the center of a solenoid, and when you switch on the electric current, it will generate a magnetic field inside the solenoid, and that magnetic field will actually magnetize the soft iron core considered as an electromagnet. So let us watch one video which will give you information about the comparison between magnetic field lines of a bar magnet and a solenoid.
Magnetic field in a solenoid. Let us study what is a solenoid. An insulated copper coil is wound around some cylindrical cardboard or plastic tube such that the length of the coil is greater than its diameter. Then it behaves like a magnet when an electric current flows through it. It is called a solenoid. Look at the figure of a solenoid. When an electric current is made to flow through it, then each turn of the coil behaves like a magnet. In figure A, current is flowing into the coil in clockwise direction. So, the left-hand side of each turn of the coil acts as south pole, whereas right-hand side of each turn of the coil acts as north pole. In figure B, current is flowing into the coil in anti-clockwise direction. So, the left-hand side of each turn of the coil acts as north pole, whereas right-hand side of each turn of the coil acts as south pole. Thus, the situation becomes similar to a number of small bar magnets placed end to end with their opposite poles facing each other, such that they collectively act as a bar magnet. Thus, a solenoid behaves like a bar magnet. So it is clear that if the number of turns in a solenoid increases, then the magnetic effect also increases. The magnetic field around the solenoid is similar to the magnetic field around a bar magnet.